techniques perspective. So if we look into this particular circuit, there is one element is missing in values. So we have a single source, but one element is missing in values. So if you look into this particular example, we can see that the value of Vs is not shown. We don't know what's the value of Vs. But that can be the value of any resistor. So we can have one resistor value is missing, or the voltage source is missing, or if we have a current source, the value of the current source is missing. And it is possible in some circuits that you might have multiple missing elements, but in this circuit we only have Vs is missing. However, in this particular circuit we said that solve for Vs. We wanted to know what's Vs is if Ix is given to be 100 milliamp or 0.1 amp. So we know the value of Ix, but we need to solve for the value of Vs. So I call this problem to be the reverse problem to the previous one. So the previous one you find R equivalent, and from R equivalent you can find the total current, and then you can find any voltage or current in the circuit. This problem is reversed. We've given you the current Ix in this circuit, but we wanted to solve for Vs. It's the reverse of the previous problem. So the technique is basically to use KVL, Kirchhoff voltage law, or KCL, Kirchhoff current law, or Ohm's law, and the combination of R equivalents, current divider, and voltage divider. Those are basically the techniques are used if we wanted to solve for this kind of circuits. So if you're going to look into this particular circuit, we know that the current going through this particular resistor, we can determine the voltage across it by Ohm's law. Once we know the voltage across this resistor, then we can combine those three resistors that are in series into one equivalent resistance. And then we can find the current going through the equivalent resistance here. And once we know the current going through those three resistors and the current going through this 20 ohm resistor, we will be able to know the current going through this 10 ohm resistor and this 15 ohm resistor. So that's the technique for or the strategy to solve for Vs. So let's go over this circuit and see how we want to solve for Vs. Solving for this particular circuit can be very exciting. It looks like it's basically a puzzle, and we are trying to figure out each small piece of the big puzzle, and eventually we'll solve for the circuit. So it's a very exciting circuit to look at. Now I'm going to start with this resistor here. We know that the resistor here has a current called Ix, where Ix is given to be 0.1 amps. Then we can apply Ohm's law across this resistor. So by applying Ohm's law across this resistor, if the current enters from the top and is called Ix, then the plus polarity of the voltage can also be at the top, and we're going to call it Vx. Now keep in mind that Ohm's law is not just V equals I times R, but also we must be consistent with the direction of the current and the polarity of the voltage. So we're going to always keep the plus polarity of the voltage at the side where the current enters the resistor. So then under this condition we can say that Vx will equal to Ix times R2. That's by Ohm's law. So this is Ohm's law here. And we know that Ix is 0.1 amp and the resistor R2 is 20 ohms. So this will equal to 2 volts. So we were able to solve for the voltage across this resistor to be 2 volts. Now what we want to do is we wanted to combine all those three resistors into one equivalent resistance. Those three resistors are in series as they share the same current, so the same current will go through them. One definition of the series connection is only two elements share one node, only two elements. So this resistor and this resistor, they are only two resistors share this node. That means those two resistors in series, and also this resistor and this resistor share only this point. That means those two resistors are also in series. Now if you look at this particular point, you have this resistor, and that resistor. Those are three resistors share one point, so those three resistors are not in series, right? So the way you figure out if the resistors are in series is that if only two elements, if the two resistors share one node, then they are in series. So in any case, those three resistors are connected in series, so we want to find our equivalent for them. So our equivalent for those resistors, if they are in series, is going to be the sum. So it's going to be the 10 plus the 30 plus the 20, and that should be the 60 ohm resistor. So here we're going to say that our equivalent will equal to the 10 plus the 30 plus the 20, and that's basically going to be 60 ohms. We called it R equivalent 1 because that's not the overall equivalent resistance, but it is the equivalent resistance of all those resistors that are in series. So now we're going to connect the rest of the circuit, and we know that the voltage across this resistor, the 20 ohm resistor, which is this resistor, was calculated to be 2 volts. So we stated that Vx here is 2 volts. And because this resistor R2 and R equivalent are in parallel, they're going to have the same voltage. Then the voltage here going to also be 2 volts. So this voltage and this voltage is 2 volts because they are in parallel. Now if we know that the voltage across this resistor, the equivalent resistance, to be 2 volts, and the plus polarity is on the top, then we can define the current IY to enter the plus polarity of the 2 volts. Now we can solve for IY using Ohm's law. This is a resistor, the voltage across it is 2 volts. The current enters the plus polarity, going to be basically Vx over R equivalent. And when we do that, we're going to have basically 2 over 60, which will be 33.3333 milliamps. So we're going to keep in mind that those 333 will continue here, right? It's going to be like infinite representation of the threes, right? So this is the current IY, which is the current goes through the 20 ohm resistor. Now we can apply KCL at this particular node. So we're going to say that the current goes through the 10 ohm resistor. We're going to call it IZ. That current IZ will equal to the sum of those two currents, IX and IY. This is called KCL. The current enters this node will equal to the currents leaving this node. So IZ will equal to IX plus IY. So we can state that IZ will equal to IX plus IY. And now we can plug in the values. We know that IX is given to be 0.1 amps. That's IX. And IY, we just solved for it to be 33 milliamps, or 33 to be 33.333 milliamps. Or we can say that it's going to be plus 0.03333 amps. Now this basically going to give us 0.133333 amps. So we solved for the current IZ, which is the current going through the 10 ohm resistor. If the current goes from the left to the right of the 10 ohm resistor, then the voltage across it by Ohm's law going to have the plus polarity on the left. So we're going to call this voltage to be Vy. So we're going to say that Vy will have the plus polarity on the left of R1, and this voltage Vy will equal to the current times the resistor, so it's Iz times R1, and we solved for Iz to be 0.13333 amps, so we put that there, and R1 will equal to 10 ohms. So the voltage across this resistor going to be 1.3333 volts. We still have a resistor at the bottom here. We needed to find the voltage across it. So the voltage across this resistor, to find that, we need to know the current going through this resistor. We know that there is Ix going down and Iy going down. So they will leave the node through R3, and this current basically going to be Ix plus Iy, which is the same as Iz, because Iz on the top is Ix plus Iy, and the current at the bottom, Iz, gonna be Ix plus Iy. And this should be Iz, which is the same current as on the top, because the current will go through this resistor to the voltage source through R1. So it makes sense that to say that the returned current at the bottom is the same as the current going through the circuit from the top. So those two currents gonna be identical. So there is different ways of looking at it. You can say that the current will flow through this resistor is the same as the current flowing through this voltage source. That is the same as Iz here. Or we can say that Ix plus Iy will equal to the current leaving, but Ix plus Iy is basically Iz, as we stated it earlier here. In any case, the current at the bottom is Iz. Then the voltage across this 15 ohm resistor gonna be defined as the plus polarity, gonna be at the side where the currents enter. Now keep in mind that this is Ohm's law convention. We must always do that whenever we're gonna use Ohm's law. So the plus polarity is at the side where the current enters. Then now we can say that Ohm's law defines Vz, this voltage, to be Iz, the current, times R3. But we know what's Iz is 0.1333 amps, and the resistor is 15 ohms. So this basically was 2 volts. So we know the voltage across this resistor, we know the voltage across this resistor, we know the voltage across this resistor. Now we can find the voltage across this voltage source using KVL. Now when I apply KVL, basically we say that the algebraic sum around any closed path gonna be 0. So I use my convention. I say that if I enter the minus polarity, I'm gonna subtract. If I enter the plus polarity, I'm gonna add the voltages, and I always go clockwise. So I go clockwise, and if I enter the minus polarity, I subtract. If I enter the plus polarity, I add. This is my convention. There is different conventions you can use to apply KVL. So using my convention, I would say that I'm gonna have minus Vs plus Vy plus Vx, which is the 2 volts. We solved for Vx to be the 2 volts. That's Vx. And then plus Vz equals 0. So minus Vs plus Vy plus Vx plus Vz equals 0. Now we can take the Vs to the other side, so it becomes positive, but I'm going to state Vs first. So I'll say that Vs will equal to Vy plus Vx plus Vz. And plug in the values for Vy and Vx and Vz. And so Vy was 1.33 volts, and Vx was solved for to be 2 volts, and Vz was 2 volts. So the answer is basically 5.333 volts. So this type of problems is kind of interesting, where we have one value is missing. In this particular example, we have Vs is missing. So to solve for the circuit, you're going to solve for the circuit backward. And to solve for the circuit backward, you're going to apply KVL, KCL, Ohm's law, and you will be able to solve for the value that is missing. In this example, we have Vs, but other examples can be the resistor values. One of the resistor values can be missing. So you have to work the circuit backward. Now when you work the circuit backward, it doesn't have to be a single source, but you should be able to solve it, but it doesn't have to be a single source. I can have 2 sources or more, and I can be able to, or I should be able to, solve for the circuit backward. However, if we only have single source and one value is missing, that will also work. So solving the circuit backward is another circuit analysis technique that you need to be